Hello and welcome to this video. So this is a video tutorial for the class Artificial Intelligence and Machine Learning for Engineers. So what we are going to do today is to see how we can use Matlab to do some forecasting about the population of a given country. And for this, the specific topics that we are going to focus on is how to engineer new features and how to select the right features. So we are going to talk about regularization, and we are going to see how to use the Lasso method to select the right feature and avoid having an overfitted model. So in this video, I'm assuming that you have watched the previous video on using Matlab to do polynomial regression. And now what we are going to do is to see how we can go further than just polynomial regression by using the Lasso method. So in the previous video, what we use to illustrate the regression using Matlab is we try to predict the population of China by illustrating this to perform a simple regression where we try to predict the population of China as a function of the year. And so in this video, we are going to use a slightly different example. We are going to try to predict this time the population of India. But this time what we are really going to focus on is how to create the right features to predict the population of India in a way that allows us to make some extrapolation in the future to forecast what will be the population of India in the coming years. So for this, we're going to use supervised machine learning. So we need to have some data. We need to have some existing data about the population of India in the past years. So for this, we are going to rely on some data of the population of India over the past 60 years or so. So the first thing that we are going to do is to load this data. So that's always the first thing. So you need to find the data that you need for your model, which in many cases you can find those data sets available online on different websites. And then, so of course, we will start by importing this data. And the first thing that we are going to do is to first get an idea of what is the data set, what is the content of the data set by just visualizing the data, by just plotting the raw data, which is always useful to know what we are dealing with. So let's start by importing the data. So in this case, the data is inside Excel CSV file. So I'm going to read this file and convert it into a matrix. So I'm going to use the read matrix command, just like in the previous video. And so this function is using as an input the name of the file where we have the data that we want to load. So in this case, I'm going to load the data contained in this indiapop.csv file and load it into data, where data is going to become a matrix. So then once we have this, so now we have created the data matrix, which is has a 59 lines, which is going to be the information for 59 different years. And it has two columns. The first column is going to be the year, and the second column is going to be the population in millions of inhabitants. So I'm going to put the first column into X. This is going to be my feature, the year. So I'm going to say that I'm going to take all the lines of data, but only column 1, and put it into X. And I'm going to put into Y all the column of data, but I'm only going to keep the feature, the second column, the population in millions of inhabitants, and put it into Y. So this is going to become the feature. Okay, so now once we have this, we have two vectors X and Y that contain on X we have the years from 1960 to 2018, and in the vector Y we have the population in millions of inhabitants. So in 1960, the population was slightly more than 400 million inhabitants, and in 2018, the population is now at about 1.3 billions inhabitants. Okay, so now let's visualize those data. So that's always useful, just to make sure we haven't done anything stupid when loading the data. It's always useful to visualize them, and just by looking at the data, you can already get quite a lot of feelings about what should be the right method to interpolate those data, to try to build a machine learning model. So it's always useful to visualize those data whenever we can. And in this case, it's pretty easy because there is only one feature and one observation. So it's going to be pretty easy to just visualize this data. So this is the second thing we are going to do. We are going to visualize the data. So in this case, the only thing that we are going to do is just to plot y as a function of x. And for example, we can plot it with some symbols like this. And so we are just going to see what the data set is about. Okay, so here we have the data. So it's a much cleaner data than last time. So we have here the population on the y-axis in millions of inhabitants, starting from 400 millions to 1.4 billions. And on the x-axis we have the year. So in this case, so this is the data that we are going to use, and this is what we are going to use as a training set to build a machine learning model. And the hope is that at the end we can have a model that can predict the population of India as a function of the year, and that we can use this model to do some forecasting to predict what will be the population of India in 30, 50, 60 years from now. Okay, so the first thing that we are going to do first is just to redo what we did last time, which is just to simply use polynomial regression, just to see. It's always a good first exercise to see could the data be simply fitted by a polynomial regression model. So we're going to start with just polynomial regression, just to have an idea of what kind of polynomial degree would be needed to interpolate this data. We can already get some feeling just by looking at the data themselves that you have here an inflection point. You have a function that is initially convex and eventually become concave, like the rate is slowing down. So if you want to fit this types of function, you will necessarily need a degree-free polynomial at least in order to be able to have this kind of inflection points. So let's try to see what it looks like. So for this, we are going to reuse the Polyfit function from last time. As a reminder, the Polyfit function, you have to pass as argument x, the feature x, the input x, then the variable y, and then you have to put the degree that you want to use. So let's just, for the sake of example, let's start with a degree 0, which obviously is not going to be complex enough. And then we are going to see what this types of regression predict. So Polyfit is going to calculate the degrees of the polynomial regression. So we are going to then store those coefficients into the variable p, where p is going to be a vector with the coefficient associated to every polynomial degree. So again, we talked about this last time, so I'm just going to go fast here, and then I'm going to see what this model predict by using the polyval function, where the polyval function uses as argument those coefficient p, and then is going to multiply it by x in order to generate a predicted value for the observation y. And then we are going to plot those data. So we are going to start by plotting the raw data first. So we can do it like this, and then we are going to hold on and start plotting the data predicted by the model. So we're going to now plot the predicted values of y as a function of x, and we are going to hold off. Okay, so let's see what we get with this. So obviously, if I just choose a degree 0, then a degree 0 is just going to be a constant, and obviously the constant is not going to fit well my data. So now let's go to a degree 1. Degree 1 is going to fit the data by a linear curve, which would simply assume that the population of India is growing linearly over time, which obviously again looks too simple, because clearly we see that initially around 1970 the rate of the population growth is increasing. You have a convex function, and then at the end towards the 2010, year 2010, we see that the function starts to become concave, which means that the rate of the growth starts to decrease, and a linear function is not going to capture this. So let's move to a quadratic function. You see that the error message from the warning message from Matlab, which we described last time, which comes from the fact that we have not normalized the data. So we're not going to worry about this just now, but we are going to need to normalize those data in a few minutes. So now if we use a quadratic function, a polynomial degree 2, again we see that it's not just complex enough to fit the data. The degree 2 is going to predict either a fully concave function or a fully convex function, but it cannot predict an inflection point like this. So we need to start to move to a degree 3. And now if we move to degree 3, now the degree 3 is fitting the data pretty well. So based on this, we could say that a degree 3 is the minimum polynomial degree that we need in order to properly fit this kind of data. So let's just see if we just simply use this this polynomial model that we just trained. How well does it work if now we're trying to predict the behavior of the population of India in the coming years? So now what we're going to do is, now that we have trained our polynomial model, we can interrogate this model. So we are going to define a new input, which will be now the years in the future. So we're going to interrogate what the model is predicting for the future. So we are going to say, I want to predict what happens between year 2000 up to 2100. So this is the range of years that I want to see what the model is predicting. So from 2000, 2001, 2002, 2003, etc., up to 2100. So this is going to become my new input, and I'm going to see what the model is predicting for this new range of inputs. So for this, I'm going to calculate what the model is predicting in the future based on those inputs. And again, for this, I can just use the polyval function. And this time, I'm going to say that I'm going to still reuse the coefficient p that we just trained. P is capturing the model that we just trained, but this time I'm going to multiply p not by x, but by x future, so that I can see what the model is predicting for the future. And same thing, now I'm going to plot what the model is predicting. I'm going to compare it with the raw data. So let's start by plotting the raw data, and I'm going to plot now what the model is predicting. So for this, I'm going to plot on the x-axis the future years, and on the y-axis the predicted value. So the value of the output of the model, but for the years in the future. Okay, and hold off. Okay, so let's see what the model is predicting. So as you can see here, it's not very realistic. So at the beginning, it looks like the prediction is reasonable, but what this model would predict is that by year 2050, the population of India would actually start to decrease, and then this population would become negative, which is not very realistic. Okay, so if we want to make a more informed prediction, if we want to make a better choice when doing some forecasting, so here what we were doing is forecasting the population of India. If we want to do a better job, we need to be smarter in the types of function that we are using to fit this data. If we just fit it by a degree-free polynomial, a degree-free polynomial is a very complex function, which is probably going to fit the data pretty well, but it's not going to be a very robust function for forecasting, because when you have a degree-free, the degree-free will necessarily start to predict some large variation when x becomes very large. If you have a degree-free function, then necessarily it will go towards plus infinity or minus infinity when x becomes very large, and it's going to quickly tend to plus or minus infinity as x is increasing. So it's a type of function that is not going to work very well to make some prediction, because it just there is too much variance in these types of function. So if we want to predict more robustly the population of India and how it's going to change over the years, we need to define some new features. We need to do some feature engineering. We need to come up with some new features, and then we are going to use the Lasso method, the regularization method, to try to select on its own what are the features that Lasso thinks are the best to predict the population of India. So let's do that. So the first thing that we are going to do here is to create some new features. So we are going to do some feature engineering. So we are going to create new features. And when we are going to do this, we can just create any feature that we want, and then we are going to let the model choose the feature that it prefers. So for this, we are going to just define a function that is going to transform the feature x and transform it into a whole range of new features. So we're going to do a little bit like the same thing that we are doing in polynomial regression. When you do polynomial regression, you start with x only, and then you are going to transform x into x squared, into x cubed, into x to the power 4, power 5, etc. So this is already some kind of feature engineering. You are introducing some new features, x squared, x cubed, x4, etc. And then you see if those features are actually helping or not. But what we are going to do here is to define a broader range of features that are more that can bring more useful information. So we are going to define some features like x squared, but also maybe 1 over x, maybe exponential x, maybe log of x, maybe the square root of x. So those are some kind of possible mathematical transformation of x, and we are just going to define all those whole range of new features by doing some mathematical transformation of x, and then we are going to let the model decide which mathematical transformation appears to be the best, or which ones combined with each other appears to represent the data the best. So for this, we are going to define a new function, because this is something that we are going to do several times. So we're just going to define a new function, and we are going to write a function that can take as input the feature x. So x is going to be the input of the function. So let's call the function make new features. So this function is going to take the feature x as input, and then is going to transform this feature into a new feature x new, where x new is going to comprise different types of features. So not just x, but also x squared, exponential of x, log of x, etc. So the first thing that we are going to do is first to normalize this feature x. So normalization, we talked about the importance of feature normalization last time. So it's pretty important to make sure that all the features have the same range to make sure your optimization is as efficient as possible. So what we are going to do is to take the variable x and just normalize it by the min-max method, by removing the mean and dividing by the extent of the range. So we are going to define a new feature xx, which is just going to be the initial feature x, where we are going to remove the minimum of this feature x and then divide by the max minus the mean. So we are going to do this, but we need to make sure that we do the same transformation for all the features. Like once we define some new features, we are going to train the model with those new features. Later on, if we want to interrogate the model with some new features, for example, some new values of the year, we need to make sure that the transformation remains exactly the same. If we train the model with a certain types of transform features, then this is what the model expects to get as input. And so we need to make sure that in the future we are able to do exactly the same transformation again in order to be able to interrogate what the model is predicting. So if we want to do this, we are going to, in this case here, take x and remove the minimum value of x. But in the future, if we want to do this again for some new values x, we need to make sure that the minimum value of x is still going to be the same value that we used to create those features that we are going to use to train the model. So for this, I cannot just say to write the mean of x here. So if I do this, so I would take the variable x, remove its minimum value. So now I would define a new variable xx, which would necessarily start at 0. So which is good. This is exactly what we want to do, but we need to make sure that in the future, if we do this transformation again to some new features, some new input variables, the transformation cannot depend on the value of the minimum value of the new variables that we are using here. We need to be able to do exactly the same transformation. So here we are first applying this transformation on the year that we have in our training set, where the minimum year is 1960. So we are going to take the values of x, do minus 1960. But in the future, when we are going to try to interrogate what the model is predicting for, let's say, from year 2000 to 2100, then we still need to use x minus 1960. We need to use exactly the same transformation, despite the fact that the minimum year, when we do some forecasting, maybe will not be 1960 anymore. So if we want to make sure that we do exactly the same transformation and that this transformation doesn't depend on the minimum and maximum value of the value x that I'm going to use here, that I'm going to use as input of this function, rather than just writing the mean of x here, I'm going to say that I'm going to do x minus min x, where min x is a variable that I'm going to pass as an additional input here, so that later on when I call this function, I can make sure that I'm using exactly the same value for the minimum of x and the maximum of x. So hopefully this will become clear in a few minutes when we use this function again. So I'm going to take the variable x. I'm going to remove the minimum value, which is going to be 1960, and then I'm going to divide this new variable by the range of the possible values. So when I do this, I start with the variable x, which goes between 1960 up to 2018. Now I'm removing the minimum value of x, so it means that now this new function is going to start at 0. And now if I want to make sure that this new variable xx is going to go between 0 and 1, I'm going to divide by the range of variation of feature x. So I'm going to divide by the maximum of x minus the minimum of x. And same thing, I'm going to say that the maximum of x, I'm going to provide it as an input for my function rather than just calculating the maximum of the variable x, to make sure that I can redo exactly the same transformation in the future. Okay, so now I have a new normalized feature, the normalized version of x. And so I'm going to now define the new features x new. So this feature x new, the way I'm going to write it is now it's going to be not just a vector, but it's going to be a matrix where it will have the same number of lines as feature x. So in this case, it has 59 lines, which is the 59 years for which we have some data. But it will have more than one column, because now we will have different values, different features, and each column will be a different feature. So I'm going to start with a first column, which is going to be the first feature of my model. And in this case, the first feature is just going to be the same as the initial feature. We still need to keep the feature x as one of the features. So that's going to be the first feature, just the original value of the year x. That's going to be the first feature. In this case, it's exactly the same feature that we initially had. But rather than using x, I'm going to use its normalized version, so that now I have a feature that goes between 0 and 1. Now we're going to define a new features. So same thing, I'm going to define a feature that I'm going to put on column number 2. This is going to be my second feature. The second feature is going to be has 59 lines as well, and it's going to be stored in the second column of this x new matrix. And now I'm going to do to create some new features by doing some mathematical transformation. So the first transformation that I will do is take the square. I'm going to take the square of x. So I'm going to retake this, the normalized value of x, and take its square. Remember that in this case, to take the square, you need to use the point hat symbol rather than just the hat symbol. The hat symbol would do a vector product, not taking the square of each of the component of this vector one by one. So in this case, we need to make sure we are using the point hat operator. Then, so new features. So now I'm going to create on column number 3, I'm going to create a new features, which is going to be the, let's take the square root. So I'm going to take the square root of x, and this is going to become my third feature. So as a third feature, I'm going to use the square root of x now. New features. So on the fourth column, my fourth feature, now I'm going to take the exponential of x. So in this case, I'm just taking some random mathematical transformation. All the typical mathematical transformations, square root, exponential, log, inverse, etc. Those are all good choices to make some new features, and then we will just let the lasso method pick the transformation that it likes. Okay, so fifth feature. So now we are going to use the log. Okay, the inverse of the exponential would be the log. So I'm going to take the log of x. So if I just do this like this, if I just take the log of x, there's going to be an issue, because now the variable x goes between 0 and 1, and I cannot take the log of 0. That would be minus infinity. So a common solution to this is, rather than taking just the log of x, I'm going to take the log of 1 plus x, so that I can be sure that what comes inside the log is never going to be equal to 0. So now I have a function that will go between log of 1 and log of 2. When x equals 0, you will have log of 1, and when x equals 2, you will have the log of 2. Okay, so new feature. So now feature number 6, I'm going to take, so now I can take the inverse, for example. So I'm going to take 1 over x. So if I do this again, so I'm going to take the log over x. Okay. So if I do this like this, again, it will be an issue, because x can become equal to 0 potentially. So if I take 1 over 0, that's going to give me plus infinity. So I need to be a little bit more careful. And in this case, I can, for example, take the inverse of 1 plus x, for the same reason as when you take the log. If I take 1 over 1 plus x, then I don't have any risk of dividing with 0. So let's define a new feature. So now I'm going to define, for example, as the 7th feature, I can use the inverse of the square. So yeah, the 1 over x2 transformation. So I can do 1 divided by x2 like this. But again, if I just do this, then when x equals 0, x2 is going to be equal to 0. So if I can do that, I need to avoid dividing by 0, I need to take the inverse of 1 plus x2 rather than the inverse of x2. Okay, so let's come up with a few more. So feature number 8, I'm going to take now the inverse of the square root, so 1 over the square root. So so let's take the inverse of the square root like this. Okay, so same thing, same problem here. When x equals 0, the square root of 0 is going to be 0. I don't want to divide by 0, so I need to take the square root of the inverse of 1 plus the square root. Okay, so x new, a few more features. So feature number 9, we are going to take the inverse of the exponential. So exponential minus x, so 1 over exponential x. So okay, so now I have the exponential, the inverse of exponential x. In this case, it's fine to do this. The exponential, when x equals 0, the exponential of 0 is 1. So it's okay to take 1 divided by 1. I don't have any risk of dividing by 0 in this case. And the last feature that I'm going to define, feature 10, is going to be the inverse of the log. So I'm going to take 1 divided by the log of x. Okay, so if I do this, again, if when x equal to 1, then the log of 1 is going to be 0. I don't want to divide by 0, so let me take the inverse of 1 plus the log of x to avoid dividing by 0. Okay, so this is going to be my function. So okay, so now that I have this function that is going to take x as an input and then transform it into a new a matrix that contains a whole range of new inputs. So now I'm going to use this function to create a new feature. So I'm going to create a feature x new, which is going to be all the new features that I'm going to use is this function. So for this, I'm going to use the new function that I just created, make new function, and I'm going to say that I want to transform x. So this function takes 4 arguments, the variable x that we want to transform, the minimum and the maximum value that we used for the normalization. So in this case, we are going to say that the minimum value is the minimum value of x, and that the maximum value is going to be the maximum value of x. Okay, and this function is going to take the feature x and transform it into some new features x new. So let's just see what this function is doing. Okay, so there's something wrong. So there's a typo in my function. So yeah, so I need to, this is max x, not just max. Okay, so let's retry this. Okay, so let's look at what we just did here. So we started with just the feature x. So x is the feature that contains just the years. So it's just a vector. So if I look at the size of x, it has 59 lines and just 1 column. And now we transform it into x new, where x new is this matrix where you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns with still the 59 lines, and now each column corresponds to a new features, x, x2, exponent x, log of x, square root of x, 1 over x, etc. So now the size of this new feature vector, this new matrix is 59 lines, but now there is 10 columns, where 10 is the number of the new features that we have just created. So when you do this, it's always useful to double check what you just did by just plotting those new features that you just created. So for this, what we can do is to plot the original feature x, so the year from 1960 to 2018, and see how it got transformed into x new. So we can see, let's check for example the first feature. So x new 1 is the first feature. So if we just plot this, we see that the first feature that we created is just a linear function of x. So in this case, it's just a normalized value of the variable x. We just took the initial value x, the initial years. We removed the minimum value so that the feature starts at 0, and then we divided by the range of this feature, so from like 2018 minus 1960, and now so we have a new feature that is just linearly correlated with the initial feature x, but now we have a feature that is normalized, so that goes between 0 and 1. So let's look at the second feature. So the second feature is x2. This is the square root transform, the square transformation. So now we have a feature that still goes between 0 and 1, which is the square transformation of x. Let's look at the third feature. The first feature is the square root of x. So same thing, we have defined a new feature that now is related to the square root of x. So let's look at feature number 4. So here the feature number 4, this feature number 4 is the exponential of x. So now we see a first potential issue is that now when we take the exponential of x, this feature is not properly normalized anymore because it goes between 1, this is when exponential of 0 gives you 1, and then it goes up to about 2.7, which is exponential of 1. The normalized version of x goes here, the normalized version of x goes between 0 and 1. So when you take the exponential of this normalized version of x, it goes between exponential 0 to exponential 1, which is not the same normalization. So here we need to take all of those features that we just created and we need to renormalize them one more time to make sure that they all have the same range of value, that they are all between 0 and 1. So the thing that we can do for this is to add an additional normalization. We are going to take all the features and just normalize them using the same method, using the min-max method, to make sure that they are all normalized. So we can just do this with a loop. So we can say that let's define a variable. Let's say that n is going to be the number of new features that we created. So if we take the size of x new on the second dimension, this is gonna give me the number of features that I just created. This is the size of x new. If I take the size of x new, it gives me 59 lines and 10 columns. Here I want the number of columns, so I can get the number of columns by taking the size on the second dimension. So size 2 gives me the number of features. This is the number of new features that I created. And now I'm going to do a loop on all the features from I equal 1 to n. I can take all those features and just normalize them. So I can say that, for example, I'm going to say that I'm going to define a new feature that is now normalized. I'm going to do that for each of the 10 features. I'm going to create a normalized version of itself. So I'm going to take, for each of the 10 new features, I'm going to take this feature x new, and I'm going to do this for each of the 10 features by doing this loop. I'm going to remove the minimum of this feature. So I'm going to remove the minimum value of this feature x new along I need to do this for every feature one by one. And then so let's start with this, and then as a second step I'm going to now divide it. I'm going to normalize it like this by dividing by the difference between the max and the minimum value. So I'm going to retake this thing and divide it by the max value of x new for the feature yi, and then take minus the minimum value of this new feature for feature number I. Okay, so let's just summarize what we just did here. So I'm doing a loop on all the features, all the 10 features that I just created. I take the feature, I remove the minimum value of this feature. This gives me this variable here, and then I take the same variable and now I divide it by the max minus min, so to make sure that this new feature x new norm is going to be a normalized variable that goes between 0 and 1. So now let's again restart by checking all those features one by one. So now I'm going to check those features x new norm. So let's look at the first one. So the first one is still this same function, linear function that goes between 0 and 1. This one was normalized already, so it doesn't change. The second one is the square, so this one did not change as well. The third one is the square root, so this one did not change. The fourth one was the exponential. So okay, so now this one is now properly normalized. It starts at 0 and ends at 1. So now we have an exponential transformation, but this transformation has been normalized so that this feature goes between 0 and 1. Okay, so feature number 5. So feature number 5 is based on the logarithm of x. So now we have a log transformation, but again, the feature is properly normalized. It goes between 0 and 1. 6. Okay, so 6 was 1 over x. So we did the inverse transformation. So same thing, looks good, normalized between 0 and 1. 7. 7 is the 1 over the square of x, so looks good as well. It's a new feature that goes between 0 and 1. Then we have the 1 over the square root of x on 8, so this feature here looks good as well. 9. Okay, so 9 was the inverse of the exponential, so this is exponential minus x in a normalized way as well, and this one is not good. So here clearly there is something wrong with this feature, so let's double check feature 10. Okay, so here the problem is that we are taking the log of x, but x goes between 0 and 1, so we cannot take the log of 0, so we need to do the log of 1 plus x. So here we need to take the inverse of 1 plus the log of 1 plus x to make sure that we are not dividing by 0 or that we are not taking the log of 0. So let's see if that helps. Okay, so now we have a new features that goes between 0 and 1. Okay, so we have a whole range of new features, and now what we are going to do is to use those new features to make a linear regression. So the first thing that we can do before using Lasso, we can just see what this is giving us if we try to do a multivariate linear regression. If we directly try to take all those new features that we just created and use it directly to predict y by using a multivariate linear regression, how well does it work? Are the new features that we created, are they useful in predicting the observation y? So the first thing to do is we are going to use just a multivariate linear regression. So let's see. So we are going to start with a multivariate linear regression, and so far we are just going to we are not going to use any validation set. We are not going to use Lasso. We're just going to see if those features that we created can they at least interpolate the data well. So for this, what we are going to do is to use the mvregress function. So the Polyfit function that we saw before for polynomial regression, it only works when x has a dimension of 1, when there is only one feature, and then it can transform this feature and create some new features as x squared, x cubed, etc. But it would not work if you have more than one starting feature. Now we have 10 features, so we need to use multivariate linear regression, not simple linear regression. So for this, it's nevertheless the same idea. We are going to use the mvregress, which is multivariate regression function from Matlab. This function takes as input the inputs x, so the observations, the feature x. So now we are going to use the new feature x that we just created, so the x new norm, X new norm is going to be the inputs of this model. This is going to be the new feature, the normalized version of the new feature that we just created. And we are going to train it to map those new features to the observation Y. And the model is going to be trained by Matlab. And what Matlab is going to give us is the coefficient beta, where beta is going to be the coefficient of the linear regression. So for each of the feature, so now we have 10 feature, x1, x2, up to x10. So it's going to give us, it's going to express y as a linear function of x1, x2, x3, etc. And it's going to give the coefficient in the vector beta. Okay, so let's see what this is giving us. So if you do this, it has created now a new vector beta that contains the value of the coefficients. So if you look at this, you find that here a list of coefficients. If we look at the size of beta, oops, yes, so the size of beta is a vector 10 by 1, which means that you have now 10 coefficients, which is the value of the coefficient for associated with each of the features. So if you have, you start with your new feature, so let's just write it like this. You start with your feature, the new normalized version of the feature, which is going to be x1, x2, x3, etc. up to xn. Those are the n features that we created. What this function is giving you is the 10 coefficient. It's going to say that y is a first coefficient b1 times x1 plus b2 times x2. So like this, so b2 times x2, etc. And it's going to do this for all the features. So it's going to give you at the end the bn times xn. So when I say xn here, I don't mean that it's x to the power n, I just mean that it's the feature number n that we just created, which in this case the feature number n is the inverse of the log. So here there is something missing. Here we don't have any intercept. Ideally we want to have an intercept b not like this, but again if you just use the multivariate regression method from Matlab, it will not assume that there is an intercept. So we need to have an intercept. We need to do it in the same way that we did in the lecture. We need to add a new column in the feature, a column that is entirely made of 1. So we need to create a new feature which is just always equal to 1. This is going to be the feature x0. It's always going to be equal to 1. And that way this new feature is now going to be associated with a new coefficient b naught, which is going to be the value of the intercept. So for this we need to just add a new column at the beginning, which is just going to be made of 1. So one way that we can do this is to start with this feature, this range of feature, this matrix. And what we can do is to concatenate this matrix with a first column that is entirely filled with ones. So we start with this feature here, which has 10 columns. And what we want to do is to add here a first column at the beginning, which is entirely be filled with ones. So the way we can do this is to create a new feature, which is a concatenation of a first column that is entirely made of ones. So this column 1 must have m lines, when m is the number of the number of different observations that we have. So we need to define this value m. M is going to be the length of x, for example. So m is going to be just 59, which is the number of different training examples that we have, and just one column. So here, when we do this, we create this vector once. This vector once is just going to be a vector. Let me define this value first. So m is going to be the number of features, which is the number of observation, which is 59. And then if I define this one, it's going to be just a vector of 51 times the number 1. So just a column with 51 values, 59 values entirely made of 1. And we want to add this column in front of the existing matrix containing the features. So if we do this, what it's going to do is we're going to take this all those features, those 10 features, and add in front of them a first column that contains just one. So just to make it explicit, so we start with this, which is the matrix that contains the feature, and now we are going to create a new feature like this, where we still have here the 10 original feature, and now we add in front of them a first column that is entirely be made of ones, which is going to allow us to have an intercept in our model. Okay, and now we are going to train the model to map this new 11 features to variable y, and now it's going to give us not just the 10 coefficient associated with the features x1, x2 up to xn, but it's also going to give us the value of the intercept. Okay, so let's make sure everything is running fine. So now it has created a new vector beta that contains all the coefficients associated with each of the features. So let's just look at the size of beta. So it has now 11 values, 11 coefficients. So the 10 coefficient associated with the 10 features plus one intercept. And then let's just see what the model is predicting. So same thing. So now if we want to get the prediction, we can use this those beta and re-multiply them by the inputs of the model, by the features in order to get the prediction from this model. So we have a vector here beta that contains the value of b0, b1, b2, etc. If we want to get the predicted value, we need to multiply those coefficients b0, b1, b2 up to bn. We need to multiply them by the values of the feature 1, x1, x2, etc. Okay, so for this we will need to do a product of matrices. So the way we can do this is we want to define a new vector which will contain the predicted value, and for this we need to calculate for each of the values for the features. So for each of the value of the features, for those normalized features, remember that the model was trained based on those normalized features, so we need to interrogate the model based on those normalized features. So we are going to multiply them by beta, and this is going to give us the predicted value. So here when I write this is actually a matrix product. Why? Because what we are doing here is that we have first the features. The feature is a vector that has 59 lines and 11 columns. I'm going to multiply this to do a matrix product with beta. Beta has 11 lines and just one column. So now I can take a product of those two matrices. I can take this product because the first one has 11 columns and the second one has 11 lines. So I can take a matrix product, and what it's going to do in this case is that for each of the features, for each of the values, for each of the training example that we have for the different values of x1, x2, x3, for each of the year that we have, it's going to take all the value x1, x2, x3, where x1, x2, x3, those values are going to be different for every year. Remember that those features x1, x2, x3, those are some mathematical transformation of the year. This is the exponential of the year. This is the square of the year. This is the square root of the year. So those features are going to change for each of the 59 years that we have. And we are going to take this matrix of 59 line and 11 column, multiply it by the vector beta, which has only 11 lines, so that for each of the 59 training example that we have, it's going to take the values of each of the columns and do a matrix product, so that it calculates just like what we saw in the lecture. In order to get the predicted value, you can express it as a matrix product between the feature vector, the feature matrix, multiplied by the vector that contains the coefficients of the model. And this is going to create, in this case, if we do this, it's going to create a y-pred, where y-pred is going to be a vector that has 59 lines, which is the 59 training example, and only one column, which is the predicted value. Okay, so now we have interrogated the model. We have calculated what the model is predicting. So we're going to plot this thing. So I'm going to plot the raw data first, and I'm going to add on the same plot the prediction from the model. So I'm going to plot the y-pred, the prediction from the model. Okay, so let's see what we get. Okay, so we can see here that now, even though we are just relying on a simple linear regression, so there is just a simple linear regression, we are just using the MVGRASS. Now, because we have defined all those new features, we don't need to use a polynomial regression. Now we can very well fit those data. We have a model that is complex enough that it can fit the data even with a simple linear regression. It's because now we have created we have done some feature engineering. We have created some new features that are some mathematical transformation of the initial feature. So now the model has not just one dimension, but now has 10 different dimensions with the 10 features that we created. And now it's able to interpolate very well the data of the population of India. So the problem with this approach is that this model is going to be overfitted because it has 10 different features, and for each of those features, the model is going to find what is the best combination for each of those 10 features. But a model with 10 dimensions like this, just to predict this simple function, is most likely overfitted. And if you look at the value of the beta that this model is predicting, you see that none of those coefficients is equal to 0. It means that the model is keeping each of those 10 features and just doing a linear combination of those 10 features. So clearly it's a model that's going to be too complex. One way we can check the degree of complexity of this model is, again, to try to use it to do some forecasting, to try to predict what will be the population of India in a few years. So let's do some forecasting again. So here it's going to be a little bit more difficult than before, because now we need to interrogate what the model is predicting for year, let's say 2000 to like 2100, for example. So let's go from 2000 to 2100 like this, and I want to know what my model is predicting for this. But now my model has been trained not based on x directly, but based on the mathematical variation of x. So what I need to do is I need to take this new range of features and do exactly the same transformation that I did before, so that the model can have exactly the same input with the same mathematical transformation as before. Okay, so this is why I defined a function to calculate those new features, because I need to be able to do exactly the same transformation as I did previously for the feature that were used to train the model. So let's do this. So I'm going to do exactly the same transformation. So now I'm going to define some new features. I'm going to start with those years, and I'm going to create all the new features that are associated with those initial features by doing all the same mathematical transformation. So I can reuse the same function. So I can make the new feature. I'm going to use the same make new feature function, but this time I'm going to pass as argument of this function the feature that I want to transform. So now I'm going to use this feature x future. I want to transform it all those years from 2000, 2001, 2002, etc. I'm going to transform it again using exactly the same transformation. And since I want to do exactly the same transformation, I need to normalize those features exactly in the same way as the features that have been used to train this model. So I need to normalize it exactly in the same way. So I need to normalize those features not based on the minimum value of those features, not based on 2000, but based on the minimum value of the original feature x, which was 1960. I need to do exactly the same sequence of mathematical transformation. Otherwise, if I take this new feature here, if I take this x future feature, if I remove the minimum value, that is to say 2000, I say x feature minus 2000, then this new feature is going to become 0. And if I interrogate what the model predict for 0, as far as the model is concerned, 0 was associated with the year 1960, and the year 2018 was associated with the normalized feature being equal to 1. So if I want to interrogate what the model is predicting for year 2000, I cannot normalize this feature so that it becomes 0 again, because then the model will think that I'm interrogating what the model is predicting for the year 1960. So I need to do exactly the same normalization. I need to do minus 1960, not minus 2000. So I'm going to normalize this feature based on the minimum value of the original feature x, not on the minimum value of the x future. And I'm going to normalize it based on the maximum values of x as well. So I need to make sure I'm doing exactly the same transformation. And then same thing, I will need to do exactly the same kind of normalization. I need to do exactly the same normalization for each of the 10 new features. I'm going to normalize it exactly in the same way. I'm going to normalize it like this. But again, I need to make sure that this normalization is going to be exactly the same as the one before. Like the minimum value and the maximum value that you use need to be exactly the same as the one that you used to train the model. Those minimum and maximum value should not be the maximum and minimum value of the new feature that you are creating. It needs to be exactly the same one that were used to train the features that got used to train the model. Okay, so if I do this, now I have created some new features here that are now associated to the year 2000 to 2100. So let's just see what the model is predicting. So again, we need to add first. We need to add a first column to this to these features, because when the model expect to have a first column that is just filled with ones that is going to multiply by the intercept. So let's do this. So we start with those new features that we just created. We are going to add at the beginning a column that is filled with just ones. For this, we need to define the number of training example that we have. So here M was the number of training example. Now we are going to interrogate the model between year 2000 to 2100. So now this M2 is going to be equal to 101, which is the number of those different features for which we want to interrogate what the model is predicting. So we're going to create a first vector that is filled with 101 lines of 1 and just one column. And I'm going to concatenate those two things into a new matrix that is going to be like this, x future new 2, where I just added in front of those features a column that is just filled with ones. Okay, so now I have let's see, make sure that okay, so there is something wrong here. Okay, so here I need to make sure I do the transformation based on the new feature that I just created. Okay, so let me okay, so here let's just do it right. So now what we want to do is exactly the same thing that we did before. So we started with the new features that we just created, and then we created a normalized version of those features. So it's the same thing here. I'm creating some new features by some mathematical transformation of this value of x, and I'm going to store it into a normalized version. So let's call it like this. This is the future, the variable of the feature in the future with some mathematical transformation and normalized. Okay, so hopefully it should be right, and I'm going to add the first column made of ones in the front. Okay, and then make sure that everything runs well. Okay, so now let's see what the model is predicting for this. So let's create the prediction of the model by multiplying those feature times the beta, where the beta is still the same coefficient that we got here. This is what the coefficient that the model predicted to be the best coefficients to relate, to map the features to the prediction. So we are just going to do the same matrix product, but this time instead of multiplying the features, the one that we used to train the model, we are going to take those features in the future for which we want to interrogate what the model is predicting, multiply by the coefficient beta in order to predict what the model is predicting for year 2000 to 2100. Okay, and let's see. So let's plot the raw data to get started. Okay, so this is going to be the raw data, and let's plot the prediction from the model. So now we're going to look at the prediction in the future. So we're going to put on the x-axis the years in the future and what the model is predicting for those years. Okay, so let's see. Okay, so clearly it's still not good because initially your model is probably fitting well the data as we can see here, but then again the model starts to diverge and becomes like very, very negative. Again, it comes from the fact that here your model is overfitted. It has kept all the features one by one, and clearly this is too many features. You end up with a model that is too complex. So it's fitting the data very well, the training data very well, but then as soon as you want to generalize, as soon as you want to use this model to make some prediction, then the model is going to have a high variance and is going to quickly go towards plus or minus infinity because it's a very complex model with a high variance. So we need to simplify this model. We need to make sure it is not overfitted. So we need to remove some of the features that are not very influential, and we need to keep only the best features. So we need to do some feature selection. Now, so far we had done some feature engineering. We created some new features, which is good because now we can fit the model with just a simple linear model. But now we need to get rid of the useless features. We only need to keep the very single features that are the most influential. So this is going to be the feature selection step when we are going to use the Lasso method to do some regularization and put a penalty on the number of features that we use and try to reduce as much as we can the number of features, to try to increase as much as we can the simplicity of the model and find the best balance between having a model that is too simple with too few features, that's going to be an underfitted model, and a model that is too complex, a model that would be overfitted. So that's going to be what we are going to do with Lasso. Okay, so let's use for this. We can use Matlab as directly a Lasso command that we can use. So now we're going to move to the Lasso Regularization, and we are just going to use the command implemented in Matlab to train a Lasso model. So for this, in Matlab, what we can use is directly the Lasso command. So this command is going to use as input the features that you have. So in this case, we are going to use the new normalized feature, which is going to be the 10 different features that we created, the normalized version of those features. In this case, unlike the multivariate regression method, Lasso will generate an intercept. So in this case, we don't need to add the first column that is full of 1, because the Lasso will just create on its own a first coefficient associated with the intercept. We can just provide only the 10 different features. We don't need to provide an extra feature that is entirely based on ones. Okay, so the second thing that Lasso need is the observation y. So it's going to try to map the feature, those features x new norm into the observation y. We're going to put a few more arguments here. The next thing that you need to provide with Lasso is a few arguments. So for example, here we are going to want to say that we want to use the cross-validation method. So we are going to say that we want to use the k-fold cross-validation method so that we can make sure that the model is not underfitted, not overfitted by using the cross-validation method. And in this case, we are going to use a Freefall cross-validation. So in this case, where usually we would use a 10-fold or maybe a 5-fold cross-validation. where we would take the entire training set and cut it into k different folds, let's say 10 folds or 5 folds. But here, because we have so few training points, we have only 59 training points, we are just going to use a Freefall cross-validation, so that we're just going to take the training set, cut it into 3 folds, and 3 times we are going to train the model based on the 2 of the folds and validate the model based on the third fold. And then we are going to repeat that 3 times based on each of the 3 folds, so that we can make sure that each of the folds is at least contains about 20 points each, so that we have a validation set that has a decent size. Okay, and then, so remember that there is, for the lasso, we need to choose the value of the regularization parameter lambda, which is going to be the penalty that we put in the cost function to try to minimize the value of the coefficients, to try to put as many coefficients as possible to be equal to 0. Okay, so for this, we want to use this lasso for different values of lambda, because we don't know yet what is going to be the best value for the regularization parameter. So we are going to tell Matlab to do this for different values of lambda. We are going to do it for a whole range of values of lambda, and then we are going to see how well the model is doing for different values of lambda, and based on this select the optimal value of lambda. So for this we are going to use the lambda command here, and then we are going to provide as an additional parameter an array here, a vector that contains the different value of lambda that we want to try. So here it means that we need to define a vector of values lambda, which are going to be the different values of lambda that we want to try. So for example, let's say that the first value of lambda that we want to try is going to be, let's say, 10. So we're going to start with 10, and then we want to try, so 10 is a very large value for the regularization. It's going to put a lot of penalty on the coefficients. So we're gonna end up with a very simple model if we do this. So then we need to gradually decrease the value of lambda to put less and less penalty to the coefficients, and to have a model that becomes more and more complex gradually. So for this, we can do this with a loop to create the new features, the new values of lambda that we want to try. So let's assume that, so we have lambda 1 already, so we'll start with the second value of lambda. So let's assume that we start with lambda equal 1, and then we are going to get the next value of lambda by saying that lambda 2 is going to be equal to the previous value, which is going to be lambda 1 initially, and then we are going to decrease it by multiplying it by 0.5075. So if I do this as a loop like this, it means that initially you're going to start with lambda, the first value of lambda equal 10, then lambda 2 will be 75% of lambda 1, then lambda 3 is going to be 75% of lambda 2, then lambda 4 is going to be 75% of lambda 3, etc. So I'm going to, at each iteration, I'm going to decrease lambda by 75%. So I will end up with some lambda values that become smaller and smaller, so that I can try the lasso algorithm for different values of lambda that become smaller and smaller. Okay, so then the lasso method is going to give us some important things that we can use. So first, it's going to give us b, which is going to be the coefficients that the coefficient of the model that is predicted by the lasso method. And it's also going to give us some fitting information, which are also going to be very useful. So it's going to give us a second variable that contains some fitting information that are going to be very valuable. So let's run this to make sure that there is nothing wrong, and let's see what the model is predicting. Okay, so now it has created two new objects, B and the information, fit information. So let's run that one more time. Okay, so let's see what we have. So in B, you see that B is a very large matrix. So B is going to contain the value of the coefficient that is predicted by Lasso for each of the value of lambda that we want to try. So for each of the regularization parameter, for each of the 20 value for lambda, Lasso is going to train this model by applying the penalty lambda, and for each of those 20 values of lambda, is going to find what are the best coefficient B. So if we look at the size of lambda, so lambda has just 20 different values, and so if we look at the size of B, so B has so 10 lines. This is going to be the 10 coefficient of the model. We are just missing the intercept here, so we just have the 10 coefficient associated with the 10 features, and then we have 20 columns, which each column is associated with one value of lambda. So let's just see what we get. So, but first, let's look at what we have in the second object fit info that got created. So in fit info, we have quite a bit of information. First, we have the value of the intercept. So if I look at fit info times intercept, so fit info is an object that has different types of information that is stored. So if I look at the property intercept of fit info, it gives me 20 different values, which are the 20 different intercepts that are predicted by the Lasso method for the 20 different regularization parameter lambda. Then we have those are the different lambda that we are used by the model. We have what else? The information that we have the MSE. So this is the mean square error of the model for each of the 20 values of for each of the 20 regularization parameter lambda. In this case, this is the mean square error of the validation set, which is the one that we care. We have in this case, this is the standard error, and then we have some other very useful information. We have the value, the minimum MSE. We have the value of lambda for which we find the minimum MSE. So this is the value of the regularization parameter lambda for which the MSE, the mean square error of the validation set, is minimum. And then we have the index that is associated with this lambda. That is to say that in this case, we created 20 different lambda value. What this information is telling us is that the ninth value lambda is going to be the one that minimizes the MSE of the validation set. So it's easier to understand this by just plotting the MSE as a function of the value of lambda. So in this case, so we start with different value of lambda, different value for the regularization parameter, and what we want to find is what is the value of lambda that is giving us a model that is not too simple and not too complicated. And the way we know that the model is not too simple and not too complicated is that it's going to give us the minimum error for the validation set. It's going to give us the model that generalizes the best when you try to predict some data in the validation set that were not included in the training of the model. So for this, there is a function in Matlab that we can use directly to plot the values of the MSE as a function of lambda. We could just plot it ourselves as by putting lambda on the x-axis, and by putting the MSE that is found like this. We could say I'm going to use the fit info, and then put take the MSE that is predicted for each value of lambda. So I could do it like this, and it's going to give me the value of the MSE as a function of lambda. But in this case, it's better to just use the function provided by Matlab, because it's plotting it in a more useful way. So for this, we can use the function that is lasso plot. And so the way it's going to do is going to directly plot in a way that is specific to the lasso method, the outcome of this model. So I'll show you what this plot looks like, but it needs as argument the values of B, the coefficients of the model. It needs the fit info object as an argument, and then you need to select the type of plot that you want. So I'm going to select the plot type, and here I'm going to say that I want a cross validation plot when I'm going to plot the MSE of the cross validation. So there is different types of plot that you can create here. Those are different types of plots that are relevant to the lasso method. And then I'm going to add the legend. I'm going to say I want to show the legend, because the legend is actually useful in this case. Okay, so let's just see what the model is predicting. Okay, so here this plot is pretty interesting, because it plots the MSE of the validation set as a function of the value of lambda that we use, as a function of the regularization parameter. So here we find that when we start, the initial value for lambda is a little bit high, so it's hard to see much. So let's start with an initial value of lambda that is a little bit larger than that. So let's start with a value of 5, and let's see what we get. Okay, so it's a little bit better like this. So if we start at 5, we see that when we use lambda equal 5, we put a very high penalty on the coefficient of the model. So we're going to end up with a model that is very simple, a model that has tried to simplify, that Lasso tried to simplify the model as much as possible. So it removes a lot of features, and so you end up with a model that is underfitted. So in this case, the model has a very high MSE. It cannot predict very well the validation set, because it's just too simple. Then as you decrease lambda, so in this case lambda becomes smaller and smaller as you go from the left to the right, lambda decrease. We reach a minimum, and then the MSE of the validation set starts to increase again. So in this case, it means that now the model becomes too complicated. Now the lambda values that we are using here becomes just too small. So the model doesn't put enough penalty on the value of the coefficients. We keep too much coefficients. We have a model that becomes too complex again, and it's going to start to be overfitted. There's two ways we can see that this model is overfitted. First, the MSE of the validation set becomes larger. So it means that it doesn't generalize as well as when you use this lambda. Here, when you use a smaller value of lambda, it doesn't generalize as well. It doesn't predict the validation set as well as when you have a model that is more simple. And the other thing that you can see is that here you have the standard deviation. The standard deviation here, this error bar, corresponds to the standard deviation of the MSE of the validation set on each of the k-fold that you use. When you do the k-fold cross-validation, you are training the models k times. In this case, I'm training the models 3 times based on each of the 3 folds. So I'm going to get 3 MSE values based on the 3 training that I'm doing. So those red symbols is the average of those 3 training. And then I have the error bar here, which is the standard based on the standard deviation. So here you can see that the standard deviation becomes very high. It means that the model starts to have a high variance. It means that when I train the model based on one of the fold, the model is going to be very different than if I train it based on another fold. So you start to have a very large variability in the model, and you can see that by this high standard deviation here. So in this case, we find that this lambda here, which is highlighted in green, is the lambda for which the MSE of the validation set is the minimum, which is something that we can get with this fit info object. In this case, we find that the lambda that gives you the minimum MSE for the validation set is this lambda at that is equal to 0.66 in this case, which is going to be this lambda here, 0.66. So now you have a model. When you use this lambda equals 0.66, is going to give you a model that is not underfitted. If you use a model with beta that is for lambda that becomes too large, the model is underfitted, and when lambda is too small, you end up with a model that is underfitted. So let's just see what this model is predicting, just to have an idea of the how well this model is doing. So let's just visualize the prediction from Lasso. Okay, so what we are going to do is to say we need to take the coefficient predicted by Lasso and multiply it by the values of the features in order to see what the model is predicting. So for this, what I'm going to do is to calculate the predicted value. So for this, if I want to know what Lasso is predicting, the first thing I need to use is what is the intercept predicted by Lasso. So for this, I need to use this fit info times intercept. So, but if I do this, this is going to give me all the values of the intercept for each of the lambda values. I just want to find the value of the intercept for just the best value of lambda, the value of lambda, the value of the regularization parameter that Lasso found to be the best, like this value for 0.66. So this value is also stored here. So this is the in this case, this lambda min MSE is the value of lambda that gives you the minimum the minimum value for the MSE of the validation set. So if I want to find the among those different intercepts, which one is the good one, I need to use the index value that corresponds to the index of the best lambda. Here we have tried 20 values of lambda, and we need to pick the one that was found to be the best by the model, and we just need to pick its index, not the value of lambda, but just the number. Is it lambda number 1, number 2, number 3? And so this information is stored here. This is the index for where you have the minimum value for the MSC, which in this case is 13. So if I want to do this, I can say I'm going to use this vector with all the intercepts, but I'm only going to take it for the index that corresponds to the case where we have the optimal value for lambda. So here I'm taking all the intercepts for the 20 values of lambda, and then I'm going to take only the element 13 of this vector, which is the 13th element of this vector, is the case where you have the minimum values, the best optimal model with the lambda that corresponds to the minimum value for the MSE of the validation set. Okay, so here now we have the intercept. So now we need to take the features and multiply them by the value of the coefficient. So same thing, I'm going to take the features. So the feature are x. I'm going to reuse the feature of the model like this. Okay, and I'm going to multiply all those features, do a matrix product to multiply those features with the coefficient b of Lasso. But again, here b is just a giant matrix that contains the value of the coefficient for each of the 20 different values of lambda. So again, we are only going to get the values of b that correspond to the optimal value of lambda. So same thing, we're going to take all the values of b for each of the 10 features, but we are going to use it only for the model corresponding to the best lambda. Okay, which is only one of the different columns of this b vector. Okay, and so if we do this, this is going to give us the values that are predicted by the model. Okay, so now let's just plot what the model is predicting. So let's plot first the row value as usual. So let's just hold on like this, and let's plot now the prediction from the model. Okay, so we plot the predicted value from the model, and we hold off. Okay, so we see that we have a pretty good model here, where the values are very well interpolated by the model. So the model given by Lasso is also very good. But let's just see what it would get if you were actually using different values of lambda. So as a reminder, so in the fit info, we have the different values of lambda. So let's just see what we have here. So those are the different values. When we use index 1, it corresponds to the smallest value of lambda, which correspond to here, where the model is most likely overfitted. And then when we use the index number 20, we have the very large value of lambda that penalizes the coefficient quite a lot. So we end up in this case with a model that is very heavily underfitted. So let's just try to look at what the model is predicting. If we are not see what the model is predicting for the best value of lambda, but actually for the other values of lambda. So if we first look what the model would be predicting if we use the largest value of lambda. So if we want to see what the model is predicting for the largest value of lambda, so when lambda is equal to 5, this corresponds to the index number 20. So we can say I'm going to take the intercept number 20, multiply, and then add the multiplication between the features and the model that are the values of the coefficients when lambda is equal to 5 for index equal 20. So let's just see what it looks. So here we start to see that the model is becomes a little bit more simple, because now it's not fitting as well the data. You see that the model is still pretty good, but it's not as well fitted as when you allow a little bit more complexity. When you allow a little bit more complexity, you see that your model is much better fitted here. And now let's just see what we would get if we were using the most complex model. So if we use the most complex model, that is to say, in the case when we use index equal 1, it's going to give us the intercept found by Lasso for the smallest value of lambda, and we're going to put intercept index 1 here to find the coefficient predicted by lambda in the case of a very small coefficient of regularization lambda. And let's just see what the model is predicting. So here we have the most complex model, so it's fitting very well the data. And here in this case, we don't see any obvious sign of overfitting. It's because in this case, like, we see that the error is slightly larger, so there is definitely some overfitting, but it's still a very small error as compared to the error that we are making here. So your model becomes a little bit less good, but it's not still very obvious. Okay, so let's come back to the best model here. So what we are going to do is just to replot this this best model. So here we have the best model predicted by Lasso, which correspond to this value of lambda. And now let's just see how much the model has been simplified. So we started with each of the features. So we have those 10 different features here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are the 10 different features, the 10 different inputs for the model. And then those inputs are going to be multiplied by B. So if you look at B, you can look at how much of those coefficients are now becoming to 0. So if we look at, let's start with B when lambda is very small. So when lambda, when you take it for index 1, you have the smallest value of lambda, so it's going to give you what the model is predicting for a model that is still pretty complex. So we see that in this case you still have already some coefficient that are 0. It means that Lasso decided in this case that those features, which are feature number 4, number 5, number 6, 8, 9, 10, those features were judged by Lasso to be not very important. And now if we look at the most simple model for Lasso, for the given by Lasso for the highest value of lambda, now you see that there is only 2 features that have survived. Now there is only 2 coefficients that are not 0. It means that now you have a very simple model with only 2 different features, which in this case is just the original x and this feature. So this is 1, 2, 3, 4, 5, 6, 7. So only feature 7 and feature 1 have survived, where feature 1 was just the year, the original value of the year. And feature 7 is this 1/1 plus the square of the year. For some reason, this feature was found to be the best feature by Lasso to have a model that is accurate and that is as simple as possible. And then if we look at the model that was determined by Lasso to be the model that generalizes the best, it has skipped 1, 2, 3, 4 features. So the model that Lasso thinks is the best has 4 different features. So it has the first feature, which is x. The second feature, which was the square of x, has disappeared. The third feature was found to be important by Lasso. The third feature is the square root of x. The fourth feature was also found to be important by Lasso. The fourth feature is exponential x. This function was found to be important. And then we have the 5, 6, 7. So the feature 7, which is this 1/1 plus the square of x. This again, Lasso thinks that this feature is also important. So the more you have a complex model, the more features you have. The more you have a very simple model, the fewer features you have. Okay, so now the last thing is to see what the model is predicting when we are trying to do some forecasting. Okay, so let's see what the model is predicting when forecasting for the future. So we're going to do the forecasting again. So okay, so for this, what we are going to do is just to see again, if we just use the same model, now we are going to see what the model is predicting, but this time for the future. So we are going to reuse exactly the same model here. So we're going to use the same intercept that was predicted by Lasso to be the best intercept for the most optimal regularization parameter. And we are going to use exactly the same coefficient here, the linear coefficient that we are judged by Lasso to be the best for the model that generalizes the best. But this time, we are, rather than calculating what the model is predicting for directly the transformed feature, we are going to calculate what the model is predicting for the future, for the future. We are going to look at those future variables that we just created, which were those variables here. This is the normalized version of the transformed feature associated to the future years. So those are the one that we are going to use. This is the variable that we created by taking the year 2000 to 2100. Then we did all the same mathematical transformation to those features, and then we normalized them in the same way that we did for the feature that we use to train the Lasso model. So we need to put exactly the features with the same mathematical transformation, but now we are going to interrogate what the model is predicting for the future. And same thing, we are going to plot what the model is going to predict. So we're going to start by plotting the raw data, and by plotting what the model is predicting for the future years, and we are going to see what the model is predicting in the future. Okay, so let's just see what we get. Okay, and now you can see that we have a pretty realistic prediction. So in blue here, those are the training data. This is the data that we use to train the model. And in orange here, this is the the prediction from the model, which is the continuation of this plot here. This plot is what the model is predicting based on the training data, for the training data. And now this model, because now this model is more simple, this model has been optimized by Lasso to be not overfitted and not underfitted. Now it's a very robust model that predicts a very realistic prediction for the population of India. So what this model is predicting is that for example, in 2050, the population of India will be somewhere around 1.7 billion, and then in 2100, the population would be the rate of the growth would continue to decrease, and the population would be a little bit larger than 2 billion people. So of course, this model cannot guess the future if the politics of India changes, and if either the government is trying to limit the number of births or trying to stimulate the number of births, then of course this function can start to increase faster or can start to decrease smaller. But what this model can do is that if you just assume that the rate of the growth of India is going to still continue with the same kind of mathematical function that it has used over the recent years, then this is what the model is predicting. So this is a good way to do some forecasting if you want to predict the evolution of the population of a country in the future. Or we could also use this to predict the number of people that become sick from a given illness or something like this. So we just use historical data obtained from the past. We just try to find the function that fit the best those data. And again, if we just use a simple polynomial regression, then we can see it would not work. Like, the prediction would be completely unrealistic. So if we want to find a robust function, we need to create some mathematical variation of the features, and then use Lasso to find the most meaningful features, that the one that gives you a model that is the best balance between underfitted and overfitted. And then this model is going to be more robust in predicting what happens for the future, because this model now is not overfitted, so it doesn't have a high variance anymore, and it can offer a good, pretty realistic prediction of what will happen in the future. So this is an example of the different things that you will have to do if you want to train a robust model that is robust enough to make some prediction for the future, some forecasting. So again, of course, you need to have some good training data for this. Then you will just visualize the data in order to get some feelings about the kind of data that you have. Then the next thing is that you are going to create some new features. You are going to do some feature engineering, creating some new features. In this case, we're just going to create some mathematical variation of those features. Then you are going to normalize those features. So that's something that is important, to make sure each of the features have the same range of values. This is especially important since we are creating some new features that are the log, the exponential. Like, when you take the exponential is going to yield like very large values. We don't want the features associated with the exponential transformation to be much larger than the other features. So we are going to make sure that each of those new features are properly normalized. And then we use Lasso Regularization to select what are the best features. We need to try different values for the regularization parameter lambda. We need to find the value of lambda that gives you the minimum MSE or the minimum RMSE for the validation set. This gives you the regularization parameter that gives you the model that is not underfitted. If lambda is too high, model is underfitted. If lambda is too small, then the model can become overfitted. So you need to find the best regularization parameter that gives you a model that is not too complex and not too simple, just a model with the right penalty, and this gives you the model that can generalize the best. And then once you have this, you can use this model to do some forecasting and predict the future. Based on historical data, you can now predict what will happen in the future. And this, the key condition for this is to have a model that is not overfitted and a model that is not underfitted. So now this is what you will have to do in your as homework. You will have to use a dataset that I will give you, and you will need to come up with your own method to find the best possible model. You will need to do some feature engineering to come up with the best possible features, and then to do some feature selection to keep only the most influential features by using the Lasso method, or by doing last time using polynomial regression and trying to use a validation set to look at what is the best polynomial degree. And based on this, you will be able to train a model that shows the best balance between being underfitted and overfitted, a model that is complex enough to capture the relationship between the input and the output, but a model that is not too complex so that it can generalize well to unknown data.